Welcome to part 2 of what analyses do hydrologists do with streamflow data. This video is meant to accompany part 1, in which I covered basic analyses like hydrographs, unit hydrographs, hydrographs, why we make 3 different versions of hydrographs, flow duration curves, and calculating the hydrologic response on annual and seasonal timescales. So in this video, I'll be moving on to more complicated techniques. But picking up with the not so complicated precursor, in the previous video, I showed you that you could calculate hydrologic response on annual timescales or seasonal timescales by taking the total stream flow and dividing it by the precipitation. Well, you can do the same thing on event timescales, except that this time we want to be able to separate out base flow. So we don't want that portion of the hydrograph that doesn't reflect the storm to be calculated into our hydrologic response when we're thinking about the response to an individual storm. So our hydrologic response function then is a storm flow divided by precipitation. And this is useful if we are wanting to understand storm-to-storm variability within a watershed, how seasonality or soil moisture conditions might affect the response. But you might be thinking to yourself, now we need to define something new. We need to define storm flow, and we need some way of splitting that out of the stream flow data. So there are a couple ways we can do that, but the classic way of doing that is what's called a graphical hydrograph separation. Now, this isn't always drawing lines in actual graphic form. A lot of the time, this is writing code or writing equations to do it with your streamflow data. But the general principle is that you have some sort of hydrograph and you draw a line through the hydrograph that separates out base flow below the line and quick flow or storm flow above the line. And then you look at that and calculate the volume of storm flow, so the volume of stream flow above the line, and that gives you your storm flow. So these graphical methods have been used for a long time. They were really important from the 1930s through the 1960s. They are still used today. They have a number of different forms. You can see 2 of them illustrated here. These different forms depend on the assumptions that we make about how base flow responds to precipitation. So even though it's base flow, that groundwater system is still feeling the effects of the precipitation. And so it does tend to increase during the storm, and these different shapes of the lines depend on what we think that is doing. So one of the simplest methods, and one that is still used today, was proposed by Hewlett and Hibbert in 1967, and they said, just take a straight line with a slope of 0.05 cubic feet per second per square mile of drainage area per hour. That's not so bad. Let's see what that looks like in practice. So this is a storm hydrograph for West Creek at Pleasant Valley Road near Cleveland, Ohio, in November 2012. So we start our hydrograph separation at the beginning of the rise of the hydrograph. We know our stream flow area, and we work out the rate or the slope of that line, and we go up by that slope, and you can see the equation worked out here, continuously until that line intersects the falling limb of the storm hydrograph. And then we stop and we say anything above that line in this region is storm flow, anything below that line is base flow. Now, just as one note, I did this for a small watershed, and I did this with the unit or instantaneous data, but a lot of the time that we're doing these graphical separations, we're doing them with daily data. Well, okay, 0.05 cubic feet per second per square mile per hour. That seems a little arbitrary, as are all the other shapes. And in fact, Hewlett and Hibbert themselves said that hydrograph separation is one of the most desperate analysis techniques in use in hydrology because we had so little physical basis for choosing the shape of that separation line. Alan Freese, famous groundwater hydrologist, said hydrograph separation appears to be little more than convenient fiction. So why did I just teach you about it? Why are we still using it? We often teach it in engineering hydrology classes, and it can be really useful for comparing runoff across a fence in that hydrologic response function or in different watersheds. So if we just need to say, how does this watershed compare to this other watershed in terms of the way it responds to storms, then we don't need a physical basis. And so a graphical separation technique can work pretty well. However, as Hewlett and Hibbert and Freese were getting at, these graphical hydrograph separation techniques don't tell us much about the processes actually happening in the watershed and why the streams might respond differently between different storms or across watersheds. They don't tell us anything about streamflow generation mechanisms. So if the classical graphical hydrograph separation is little more than a convenient fiction that doesn't tell us anything about process, what can we do to make it better? In order to make it better, we need more information than just the stream flow. We need some sort of tracer that tells us about water that comes into the stream during a storm via different flow paths or via different processes, or that has a different history associated with it. We can use things like salt, and electrical conductivity. We tend to have higher electrical conductivity water in groundwater, where the water has been in contact with rocks and soils for a long period of time, than in precipitation and water that's spent a short time on the land surface. So if we watch how conductivity changes over the course of the storm, we can add that to our streamflow data to separate out a hydrograph between water that's had a longer residence time in the ground and water that's had a shorter time in the watershed. We can also use the stable isotopes of water itself to do a similar separation. And the mechanics of how we actually use these tracers and do the separations are beyond what I'm going to talk about today, but I want to give you an illustration of what that allows us to do. So as shown in this example hydrograph here, one of the ways we can use tracers to do a better hydrograph separation is allow us to separate old water and new water in the stream during the storm. So these approaches with isotopes at first and then other tracers in addition to isotopes to separate hydrographs were really, really revolutionary to our ideas about how water gets to streams, beginning in about the late 1970s. And if you think back to all of the discussions we had about streamflow generation and shallow subsurface stormflow and saturation overland flow and groundwater, all of our understanding of those processes were helped by this idea of hydrograph separation using isotopes and other tracers. So let's define a few things. So new water, when we're talking about a hydrograph separation, is water that has come into the stream from precipitation during the current storm, during the storm that we're measuring or doing the hydrograph separation. Old water, then, is everything else. So it's any water that was stored in the watershed before the current storm. That could be water stored in the soil. That could be water stored in the groundwater aquifers. That could be water stored in lakes and ponds. Doesn't say anything about how long the water has been stored. Transit time analyses are a whole nother kettle of fish, but here we're just making a separation between new and old water. Note that I still am not telling you anything about subsurface storm flow versus saturation overland flow and those other streamflow generation mechanisms. But by knowing how much water in the stream is new and how much water in the stream is old, we can start to infer these streamflow generation mechanisms. If you think about, for example, infiltration excess over land flow, water that's never getting a chance to infiltrate in the soil, running off quickly to the stream, that's one way that we get new water into the stream. So if we see a hydrograph with a lot of new water in it, then we have some information that we can combine with the other things we know about the watershed to understand that maybe infiltration excess over land flow is important in that watershed during that storm. But here's the kicker. Stormflow is often old water. So the water you see in the stream during a storm was often stored in the watershed prior to the start of that storm. Even at peak flow, when the hydrograph's at its highest, old water is typically more than 50% of peak flow. And if we added up all the storm flow, we get about 60 to 80% old water. Okay, so that is a pretty big generalization. A lot of the studies that have been done using hydrograph separation have done it in humid climates and in forested sites and in very small watersheds. So do add that little bit of filter to the way you understand things, because there are some important exceptions. If you have a lot of wetlands or impoundments, reservoirs, or lakes in your watershed, you tend to get a high portion of old water, because those are, again, places that have relatively high volumes of old water that can be stored. And then when rain falls on those wetlands or lakes, it pushes out the old water into the stream. On the other hand, agricultural, particularly tile-drained watersheds and urban watersheds, are dominated by new water at peak flow. And that's because the development of pipes in the subsurface, storm sewers or tile drains, and a reduction in the ability of water to infiltrate into those watersheds means that water is routed very quickly from the upland into the stream, and we see more new water. Okay, so there's a lot of old water in a lot of streams during storms. How does it get there? I talked a little bit about this idea in a blog post I wrote about where I use the analogy of the hose. So if we think of the watershed as a hose, when we turn the hose on, that's been sitting outside on a hot summer day, the first water we get out is warm. So that's the old water. So as we turn the hose on at the spigot, cold water is coming out of your house, out of your tap, but the first thing it does is push the old water out. So what are those actual mechanisms, since watersheds aren't actually hoses? One is saturation over land flow via return flow. So this is the water that's been in the surface as subsurface storm flow and is now coming back out to the land surface where the water table intersects the land surface. Another is subsurface storm flow and water stored in macropores and within the soil matrix between storms. Another reason that we get old water is this idea of a transmissivity feedback, which is a function of how hydraulic conductivity decreases very rapidly with depth, resulting in a perched water table that hangs out between storms and then can be mobilized in subsequent storms, slowly working its way to the stream. The other thing is that near the stream, you typically have soils close to saturation. So then when water starts to be delivered to the riparian zone during a storm by subsurface storm flow or by overland flow, the water table rises rapidly. And as that water table rises rapidly, older water is released to the stream. And so we call this groundwater bridging. You can learn more about how streamflow generation mechanisms are tied to hydrographs, the difference between a hydrograph response and transit time by looking at the blog post I've linked here, and a whole series of videos that I've made on streamflow generation mechanisms. All right, So we can separate Stormflow out and start to understand those processes by using tracer-based hydrograph separations. But sometimes we want to understand what's happening in the groundwater in a watershed and how that's supporting base flow. And so note that this illustration here kind of looks like a hydrograph separation, but now we're really interested in the slowly changing base flow component of it. We call this a recession analysis. And what a recession analysis does is it looks at the shape of the fall in the stream flow on the falling limb or declining limb of a storm and during the base flow period between storms. And what you see in this illustration is that there's this really quick fall in the stream, and here they're calling it quick flow. We might think of this as overland flow and really rapid subsurface storm flow. And then there's this inflection point here, and the hydrograph falls more slowly. They've labeled this interflow, so this is the slower flow paths of subsurface storm flow. And then there's yet another inflection point here, and from there it falls even more slowly, and that is base flow supported by groundwater. And so what we could do is we could measure this change or the slope of the curve at different times. And we could even break it up into different segments that we think are defined by these inflection points and might tell us about different processes. We can, during this base flow period or during each of these recession components, we can fit an equation to the hydrograph. And what this equation typically has is a form something like here in the red box, where discharge at a particular time is a function of discharge at some initial time, time 0, times an exponential that reflects the difference in time between when you're interested, t, and time 0, and a constant with a negative slope to it. So this is just saying, what is this slope that is happening in this recession curve? So again, we can fit this sort of equation to the falling limb and base flow periods of our hydrograph. We can use those to understand how quickly storage is draining in the watershed. We can actually, making certain assumptions, calculate aquifer parameters from this. We can also think about shifts in this recession behavior as reflecting groundwater recharge. Now, there's a whole lot of details underneath what I just said, and we're not going to get into it. But if you wanted to use streamflow data to understand groundwater in a watershed, recession analysis is a great tool that you have available. What else can you do with streamflow data? Well, sometimes some people are interested more in the water quality than in the streamflow itself. And so if you have water quality samples or sensors in the stream, you might get a nice time series of nitrate concentrations or chloride concentrations or turbidity, how muddy the stream is. But if you want to explain why those concentrations are changing over time, then it's really helpful to have the streamflow data. So this is just an example of some data from my own work. The yellow dots are turbidity in a stream for about a 6-week period. And what we see is that when we get these spikes in turbidity, but these spikes in turbidity all align with the spikes in streamflow. So over here on this axis, curiously enough, our units work the same. So we have the black line is discharge in cubic feet per second, and the yellow dots are turbidity in NTUs, which is the turbidity units. And we see them going up and down at the same time. So now we can say, hey, the high turbidity periods in the stream are associated with storms. And between storms, then we can see that the stream is running more or less clear. So now we can have some understanding that we might be able to use to explain the sources of the muddiness in the water. We can go a little bit further If we want to actually think about the flux of dissolved or suspended materials, not just the concentration, but the actual mass moving through the stream, then we can calculate a load. And a load is simply the concentration times the discharge. And again, we can do that over multiple time points, any time point that we have a sample for. And so we can think about the number of kilograms of mud being exported by a stream over, say, a 6-week period. And that lets us then think about the impacts on receiving water bodies, like how much sediment is coming into this lake, or how much road salt is going past the water treatment intake and potentially affecting the corrosivity of the drinking water. Another thing that we can do is we can use streamflow data to help us build and test hydrological models. So these are numerical, computer-based models that let us ask what-if questions about realities that don't exist. So for example, this is the West Creek watershed, again, near Parma, Ohio. This is a watershed where they're very interested in the impacts of stormwater and stormwater management on the stream. And so we have been building hydrological models that let us ask questions like, what happens if everybody puts a rain garden in their front yard? How does it change the stream? So we use a lot of GIS data, data on land cover and soils and topography and existing stormwater management and pipes, and we represent the model as this series of small hydrologic response units, essentially dividing the watershed up into small areas that are each characterized by their watershed characteristics. And then we use rainfall data to rain on that watershed and generate a hydrograph. But if we want our model to be realistic, we need to know whether that hydrograph we're generating under the existing conditions is realistic. So we use streamflow data. Here we've got a USGS gauge at the outlet of the watershed, and we use it to calibrate our model. So essentially to tweak the way we are representing the processes in the watershed until what our series of mathematical equations, our numerical model, gives us matches reality. And then once we've matched reality, we say that the model is calibrated, and now we can finally go in and say, okay, now we don't have very many rain gardens in this watershed. Let's add 10,000 rain gardens, and how will the hydrograph change? And it makes us feel more confident in the results of the model because we know that the model was able to reproduce the existing reality. So watershed models can be useful for answering questions about more speculative scenarios, but they can also be incredibly useful for answering really practical questions like, is it going to flood next week? And this is where we can combine weather forecasts with models of the watershed calibrated to USGS streamflow data to actually predict or make flood forecasts. So the National Weather Service in the United States operates 13 river forecast centers. And these river forecast centers have a specific area they're in charge of. So we're in the Ohio River Forecast Center here. And the forecasters at the Ohio River Forecast Center are going to be pulling in stream gauge data. They're going to be looking at satellite data for the amount of precipitation likely to occur, radar data, weather stations, weather models, supercomputers, all the fancy stuff to make predictions about whether flooding will occur, and if it occurs, how high it occurs. And so every day, these river forecasters are generating forecasts for 4,000 locations throughout the United States, and they're doing them on timescales of hours to months. And then when flooding is predicted, the National Weather Service can issue a flood watch or a flood warning. They can be in communication with emergency managers. They can say, hey, Grand Forks, better step up the sandbagging because it looks like the Red River is going to crest higher than expected. And so these river forecasts are examples of watershed models that have this really practical, immediate application, and we use the streamflow data to check the performance of these models and make adjustments in real time.